title of my work is Ligand-free alloy nanoparticles for applications in nano-toxicological assays. So the first thing we have to ask ourselves is, or I want to introduce you to, is actually why do we want to study alloy nanoparticles in toxicological assays? Or actually, why is this relevant? The main thing we had in mind in this context was risk assessment for medical implants. If you can imagine, we have an implant, like for example, When we have, for example, alloy material, like for example, a stent or a bone implant, this is usually made of an alloy material. And when we know that these materials can be in the body for quite some time, let's say they can be in there for months or even years, then there's always the risk of alloy wear debris. So some alloy wear debris can be released to a biological system, and up to now it is completely unknown how toxic this material can be over time. This is particularly critical as it is known that nanoparticles, which are found in the bloodstream, are known to cross biological barriers. They can, for example, cross the blood-brain barrier or even enter the testis or the fetus. So this is something which has caused great public concern. This even made the FDA to release on its homepage a deliberate warning on the risks of artificial hip implants and the problems of wear debris. So we want to study these effects. The question is, how can we do it? When we want to study this, we need appropriate materials to mirror these effects in specific, which is we need to have implant wear materials, nanoparticles, which are indeed alloy nanoparticles. So the question is, how do we get those? And what are the requirements for them? First, let's start with the requirements. What do we need to study these effects? At first, we need to have controlled particle properties. We need to have the particle size controlled, as well as the composition. And the tested material must mirror the exposure scenario. This means we have to test exactly or similar materials which can also be found during implant ablation. This leads to another prerequisite, which is very important in this context, which is actually that we have to have the particles free of any artificial ligands. Because we have an implant material in our body, and any artificial ligands we would have in our nanomaterials, which we test, when we, for example, make our materials by chemical synthesis in the presence of some artificial polymers, then these would be disturbing components which would actually compromise our toxicological assay. So what we need is actually we need ligand-free nanoparticles, which have molecules in their vicinity, which are also present in the biological system. So how can we get these particles? One very convenient method to synthesize them is the process called pulsed laser ablation in liquids. This is a physical method which is based it's actually very simple. We have a target, like a metal or whatever material we want to have, put it in the bottom of a beaker, have it in water, and then we focus a pulse laser beam on this target, and we generate our nanoparticles. Actually very simple. It's highly flexible on the used material. We can almost any material we can buy as a plate, we can transfer into nanoparticles. They are 100% ligand-free, and they are stable in aqueous media. However, there's one drawback of these materials, which is usually we have very broad particle size distribution in general. So this is the first topic I want to address a bit, which is the particle size distribution of these materials. And in order to control this, we had one idea, which at first may seem counterintuitive to you, because what we did is we added inorganic salts to our ablation medium. At first you will think, okay, we have a nanoparticle and we have a salt. Most people who know about nanotechnology know when we have a salt and nanoparticle, they will precipitate, as well known. However, we studied these effects anyway. Nonetheless, we added the different ion types and different ionic strengths. And the results were actually quite interesting, because the first thing we found in this context is that actually the colloids are critically influenced by the type of ion we put in. For example, when we added something like fluoride or sulfate, then you see that the gold colloid we synthesized is actually a blue tint, which actually indicates aggregation. However, when we added some different ions, like for example, chloride, bromide, iodide, or thiocyanate, we found the same colloid had a red color. So apparently, these ions seem to stabilize, and these ions seem to destabilize. Based on this, we deduced a Hofmeister series of elements for the system, where we found that actually cosmotropic, like hard anions, seem to destabilize our colloid, while chaotropic soft ions seem to stabilize our colloids. So we can actually get size quenching and stabilization anion specific, and this works specifically with soft chaotropic anions. The next thing we observed was the concentration or the ionic strength. And here you will see something interesting because we used very low salinities. We added concentrations in the micromolar regime, and already there we had significant effects on the particle size distribution during laser ablation. And then now you will realize that actually we are far beyond or far below any concentrations which are relevant for the screening of surface charges by classical DLVO theory. So these are actually specific effects which occur below these at concentration regimes where these effects do not yet occur. We further studied this, and we saw that actually the particle size, particle diameter decreases with the ionic strength. So the more ions we added, the lower the particle size became, which could also be verified by TEM images, where we also saw that actually not only the size was changed, but also the particle size distribution. So the particles also became at a more narrow size distribution when we added more salts. Now the question is, what is the underlying mechanism? Why does this happen? We believe that it's actually based on surface charge generation during the synthesis process. So we believe that we have some kind of a specific adsorption of an ion to the particle, to the goal on the particle, which leads to an electrostatic stabilization, which then prevents further particle growth. This can best be illustrated in this graphic, because here we plot the amount of salts and the nanoparticle surface, which is stabilized by the salts. And we can clearly see that the stabilized surface linearly depends on the available amount of ions. Actually very simple. When we have a very low ionic strength, the nanoparticle surface area is low, which can be stabilized, which means that actually here the particles tend to grow on until they have a certain size, and they are rather big in this regime. However, when we increase the ionic strength a bit, when we are, for example, in this regime, then we have a larger amount of ions. So they can stabilize a larger surface area, which can actually leads to an earlier stopping of the particle growth, which then leads to smaller particles. So I could show you in this first part that to obtain ligand-free colloidal particles, we can use pulse laser ablation in liquids, and we can control our size by salts using soft ions and micromolar salinities. The next thing I want to go into is actually the composition, because we want to talk about alloy nanoparticles in the following part of the talk. So we put it to the test. We took a material which is of technical and medical relevance, which is in this case an implant steel alloy composed of iron, chromium, and nickel. Now the question is, what's the composition of the resulting nanoparticles when we do pulse laser ablation in liquid? We put it to the test, we made our laser ablation in liquids, we obtained our colloid, and then we analyzed our nanoparticles, in this case by TEM and EDX measurements, and we could verify that actually the target composition of the bulk material is retained in the nanoparticles. Here you see the composition. In black you can see the composition of the bulk, and in red the one of the nanoparticles, and you see that for all the three main ingredients of this ternary alloy, they perfectly fit. So we can actually produce nanoparticles with the same composition as our bulk material. So next thing we wanted to do is we wanted to control the composition of our alloy nanoparticles. For this we took a bit simpler system, which had with two antipodes. On the one hand side, silver, which is known to be cytotoxic, and on the other side, gold, which is reported to have a relatively low cytotoxicity. And we wanted to study whether can we the concentration in between. So we wanted to alloy nanoparticles with controlled compositions. So we took different targets with different compositions of gold, silver, and we synthesized the different alloys, analyzed them by UV vis spectroscopy, and we could clearly verify that we really have a formation of an alloy, which can be seen by that we have only one SPR peak, and it also linearly shifts with the gold molar fraction. So we can see we have an alloy with a controlled composition. We further verified this with TEM EDX, and we found similar things to the technical alloy. Here you see the gold molar fraction of the particles, here the one of the target. You can clearly see that they are actually quite a good match, so that the composition of the particles and the target are the same. The next thing we did, we analyzed the ultrastructure of the particles as well. So for this, we performed EDX line scans of these particles, and we found that the distribution is completely homogeneous. So we have a homogeneous distribution of the elements within the alloy. So we have a solid solution nanoparticle in this context. Okay, now I've told you that we can control the particle size, we can also tune the composition, and now we want to go to application a bit. The application we primarily had in mind was reproduction biology. So we wanted to examine the toxicity of these materials in reproduction biology. Why this field? Because fertilization, as you all know, is a very sensitive process where already one compromised cell can have severe effects, can lead to a complete failure, complete death of the organism. So in this, actually, one single cell counts. Due to shortness of time, I will only go into one application here, which is the reproductivity during oocyte maturation. As you all know, all oocytes, which actually have to mature, and this process is actually highly sensitive to any influences. So we have an immature oocyte, which develops to a mature oocyte, which can be monitored by the meiotic state of the cell and by the expansion of the surrounding cumulus cells. The interesting part in this case is here we have something like a functional parameter we study. We do not look at the viability of the cells, but at the functionality of the cells, which is a big difference because it's much more sensitive than the viability. So we have a functional toxicological assay we use here. Okay, we added the different particles, like different particle sizes, surface functionalization, and compositions, while I will focus on the compositions here, and we studied the effects. The results are shown here. The first thing we can see is that actually the gold particles and also the gold-rich alloy particles did not have any effect on oocyte maturation. Okay, this is at first not that surprising because it's well known that gold is relatively biocompatible, so we could confirm this in these assays. However, one more interesting thing was actually that the technical alloys, like the nickel titanium or the chromium steel, also had no effect on oocyte maturation. So how could this be? I mean, we take a look at these materials. They contain nickel, they contain chromium. Why do they not influence the biological system? One explanation could be this EDX line scan of a nickel titanium alloy nanoparticle fabricated in water. What you can see in this context is that we have a material segregation in this context. We have here a nickel-rich core and a titanium oxide-rich shell, which seem to indicate that we have a pronounced surface oxidation, forming of titanium oxide on the surface, which can actually passivate the nickel-rich core, and due to this, lead to a reduction in the release of toxic nickel ions. Okay, now we switch to the part where actually we observed some toxic effect, which was for the silver and the silver-rich alloys. The silver, I will not go into detail here because it's well known that silver nanoparticles and also silver ions are known to influence biological systems, but I want to go to the silver-rich alloy because I want to point out that actually there's a steep drop from 50-50 to 20-80 actually. So here we have a steep increase in the toxicity. The question is why does this happen, and does this also occur in other biological systems? So we extended the study to other organisms and cells. So we took some fibroblasts, and we also took bacteria like S. aureus, and we also observed how the toxicity of the alloy nanoparticle changes. Here are two things are plotted. First the minimum inhibitory concentration and the toxic concentration, while of course a lower inhibitory concentration of course means a higher toxicity. First you can see that actually of course the the silver particles are much more toxic than the 50-50 composition. This at first is not that surprising because we can say, okay, in the one particles we have 100% silver, here we've got only 50% silver, only half the silver, which could say actually, of course, these are more toxic. But if this was the only thing which we could observe, then we would have a linear effect. So we would have a linear increase in this case of the toxicity. But we have a more than linear increase. So when we, for example, go from here, from the 80 to the 50, we had 30% more gold. We have a 5 times increase of the minimum inhibitory concentration. It means the inhibitory effect is less than expected by the silver content. So the silver in this context, in the same mass, is less toxic than here. This means that gold content seems to passivate the alloy nanoparticle. This is first very interesting from a fundamental viewpoint, but can also open avenues in other fields. For example, the gold content may be used to control the bioactivity of the silver, which can be interesting, for example, for antimicrobial effects. Okay, to sum up my talk, I've talked to you about laser ablation in liquids as a suitable method to generate ligand-free colored nanoparticles. Here you can see this method once again in real time and also in real sound. I didn't tune it down, sorry. Then I showed you that actually the nanoparticle size can be controlled by electrolytes, and we can use soft anions and micromolar salinities. I've shown you that we can synthesize homogeneous alloy nanoparticles based on technical materials as well as on controlled composition. I've talked to you about the toxicity in reproduction biology. I've shown you that oocyte maturation is a nice method to do it because it's a functional toxicity assay. And I've shown you that gold-silver alloy nanoparticles nonlinear influence. We have a nonlinear influence of silver content on oocyte maturation as well as on bacterial and mammalian cells. Okay, this I will conclude my talk. Thank all of my co-workers, of course, from different institutes, from our institute and our project partners from the Friedrich-Löffler Institute in Mariensee, our funding bodies, of course, German Research Foundation, and of course you for your kind attention. And I'm open.